everyone. So this is Peter. He got kind of connected with me and with our club through Michelle Naziri. And basically he's working at Resonado Labs, which is a startup that is kind of like redesigning a lot of sound technologies. One of the main things that we talked about in our kind of conversation was the flat, I think it's the FCS, like the flat core speaker technology. So really changing like the drivers, and like those are the things that people are putting into new consumer technology and that sort of thing. So kind of has the potential, it seems, to change the landscape of what's kind of able to be offered. I don't know too much about it, but that's why Peter's here, to kind of talk about it and tell us about, everything that's kind of that you've been working on, basically. So
Exactly.
I hope that was a decent introduction, but if you want to expand on that, feel free, please.
No, that's okay. That was a great introduction. Thank you, Alex. I have some slides to show, and I wanted to talk about transducers in general, kind of how loudspeakers are selected into products, and give a little background on FCS technology, but also there's a lot on the practical side that I don't think it's touched on in school in terms of like building a soundbar or building a pair of bookshelf speakers that would be very useful to know in kind of context. How do you make a speaker and what type of transducers do you use? Before I start, that would be helpful to understand how much people know about speaker drivers or transducers and things like teal small parameters.
I'm going to say you should assume nothing in terms of like teal small and that sort of thing. We've talked a little bit about loudspeaker topologies, like ported designs versus sealed versus like bass reflex, that sort of thing.
Okay.
But nothing really going into the actual modeling.
Okay. That's very helpful, and we'll get into that a little bit. Can I share my screen? It says...
Oh, that's my fault. Yep. All right, you should be good to go.
Okay. I will start with a little bit of information on Resonado Labs. Resonado Labs we are a startup. We have about 20 team members right now. We are headquartered in Chicago. Our goal is to grow to 30 team members by 2023, the beginning of 2023. So we're trying to grow ambitiously, and we're always looking for hardworking, smart, creative individuals like those from this program. Having a lot of audio experience is not necessary, and I understand that there's not. It's very hard to get practical or experience, especially on the transducer side, at school, and we have a lot of entry-level positions where there's a big training and learning component. But we're trying to get to 30 people by the beginning of 2023, and Resonado revolves kind of entirely around engineering technologies that improve the way we experience sound. The first kind of technology that we're focusing on is what we call FCS technology, flat core speaker technology, as Alex said. And we originally introduced this during 2020. The plan is to license this technology to different OEMs who make like the sound bars and who manufacture the speaker drivers for Amazon, for Sonos, for Polk Audio, for Samsung. And so we've signed a couple different licensing arrangements. This is kind of the first transducer we developed. We call it the Neomin 5 Gen 1. We're working on a wide range of Gen 2 transducers, but this is the Gen 1 and a little bit of a fancy graphic. That Gen 1 transducer has been featured in Airstream RVs. Airstream is a premium brand of recreational vehicles, maybe considered the top of line, and this is just showing a few pictures from the Resonado sound system that is in the back of the doors. We are working on a number of commercial applications beyond this that are more integrated into home audio. There's a very exciting soundbar project I want to talk about at the end of the presentation, and we'll kind of look at that from the practical standpoint. But that is using this very cool speaker driver that we've engineered called the NW7, and it kind of is a really good representation of FCS technology, and we'll get into that. I'm also in Resonado's acoustic lab. This is the measurement component. We have we have like a subjective listening room on the other side of that wall, but there's a few different pieces of equipment in here. Most of them are laser microphone setups that measure the displacement of the speaker and the input. We have what's called the Clippable System. Clippable is it's a German company founded by someone named Wolfgang Klippel. Does anyone know who Wolfgang Klippel is, or have they heard of him? He's a very famous acoustic engineer, very rooted in physics, but he's developed, and his company, Klippel, have developed the gold standard for transducer speaker driver testing equipment. And if any of you guys go work for like a Bose or any of those companies, that is the system everyone's using and lives and dies for. But to get into the next part of the presentation, for the last many years and in all types of consumer electronics products, they're using just conventional circular speaker drivers. This is something we pulled out of like a Google smart speaker, and I just grabbed it from our shelving system where we have a lot of benchmarks. But this conventional circular speaker driver is very, the design is very ubiquitous across the industry. You have right here like the speaker voice coil, right? This is the spider. The spider's the bottom part of the suspension. Then you have like the speaker cone, and on the speaker cone is this surround. That's like the second part of the suspension. Typically, most of the stiffness or compliance of a speaker driver suspension is in the spider component. The spider is typically like cotton, synthetic fabricated cotton, all sorts of special phenols, and it's impregnated with different materials to get certain stiffness parameters. But that's kind of where a lot of the compliance or the stiffness from the speaker comes. This is like your magnet, and you have your pole plate. The issue and why Resonado exists relates to kind of product development trends. Right now on the screen we see a top left, we have a Bentley, a NAM speaker and a Bentley car, like the JBL. I think this is the JBL Charge. Some of you guys might have that. This is a TV, obviously, a laptop, a soundbar. The reason all these products are on the screen is to reflect kind of a bit. There's been a lot of trends in consumer electronics and audio. To talk a little bit more about the business side, 10 years ago, no one really had a soundbar. No one had a Bluetooth speaker. Not many people had headphones. No one had a smart speaker. Maybe audio enthusiasts or people who were well off had nice floor-standing loudspeakers or bookshelf speakers, maybe a tabletop radio, but no one really had. Audio is not really around the home as a product. But so over the last decade, people have had. Audio has been mass marketized in a very special way, and we believe in a great way, in that everyone has a lot greater access to good premium audio, and now everyone has like a Bluetooth speaker, smart speaker, TV, and these devices aren't hi-fi audio speakers. They're not recreating the sound incredibly, but there's a lot of engineering that goes into these products to deliver a lot better acoustic experience than anything in the past has, and so we really look upon this trend fondly, but with it, there's been a lot of factors that have influenced the transducer. If we go back, like the conventional circular transducer, it's been used for decades, but the issue with all these products, there's new form factors. They've required the use of what we call a high aspect ratio speaker. A high aspect ratio speaker, racetrack shape, basically non-circular. And the reason you do this is when you have we'll talk about sound bars, for example. Sound bars are a device that a lot of people have in their homes now. I have a Klipsch Cinema 800 soundbar, for example. And 80% of the people at Resonado have soundbars in their homes. The trend with soundbars over the last 10 years is, excuse me, is reducing that height. You need to get it to be able to fit. You want it to be a sleek design, fit under the TV, and like you cannot have it interfere with the TV IR reader. So the max height is pretty much like 2.9 inches, but everyone's been trying to go lower and lower and lower. But when you take a soundbar and you try to reduce that height to maintain output and maintain low frequency bandwidth, by output I mean like SPL, your volume level, and low frequency bandwidth like your bass, your low end, your low frequency output, you need to maintain cone area, and you need to maintain cone area and maintain displacement. And to do that, what everyone's done is they go from like this circular driver, and then they just elongate it. And you get a much more rectangular thing like this TV speaker. The same things happen in all these industries. And in this drawer, we have 100 different of these like TV speakers, soundbar speakers. These are all conventional structure. But a lot of times what you see, and I was trying to show it, but you see they are just like keeping that cylindrical circular voice coil, but just making the speaker rectangular. Does this make sense?
Yeah, I think so. They're changing the like dimensions of one part of it, but kind of keeping the like overall structure.
Exactly. And what that does is it results in significant breakup modes, distortion, rocking modes, and you get you're trying to drive this rectangular thing from the circular voice coil. The yellow line is the voice coil. This is like from a top-down view, and you get a lot of significant negative acoustic effects. And one example is just a typical 2-inch, like a typical soundbar driver. Give me one sec. This is the soundbar. This is the speaker driver. It's a very similar speaker driver to what they use in like the Roku soundbar. That is a soundbar that hasn't really shrunk in its height, but it's a very good speaker driver. It has like a flat frequency response from 100 hertz to 20 kilohertz, and they literally just put 4 of these in the soundbar, and it sounds really good. You pair that with a subwoofer, and you get the full frequency band, and they're very efficient. When you go to a driver like this or like this, this one will like it drops off at like 4 kilohertz, for example. And so you're losing all that response from 4 kilohertz to 20 kilohertz. And it's pretty easy to add a tweeter, and tweeters are low cost. That's what we see in a lot of cases, but there's also just a lot of distortion and negative effects from this. And what FCS technology does, the reason for this, what Resonado has been focusing on is we rearrange and optimize the geometry of each component, kind of as you were saying, Alex, from the ground up. And so we kind of the key component is we're taking the voice coil from this cylindrical structure like this, and we're putting it on a planar bobbin and winding it like this. And so you get 2 magnetic gaps. Electromagnetics is not my specialty or my expertise, but you basically have this voice coil, and it sits in, these are 2 parallel bar magnets, and then you have your 2 pole plates or 2 yokes. And this voice coil goes up and down in there, and it enables us to, like the bobbin, what's supporting that diaphragm is along the entire length of the voice coil, the entire length of the bobbin. And so you can drive the speaker much more planar and much more linearly. And this page is kind of talking about each of the parts, and we're gonna go through some of the components right now. But the big value proposition is the fact that we're driving the cone, the diaphragm, with the entire length of the voice coil, the entire length of the bobbin. The bobbin is what the coil sits on, like that substrate, it's aluminum. uh, to prove this, that I'm not talking gibberish, we'll look at some laser scanning vibrometer data. Does anyone know what a laser scanning vibrometer is?
No.
It's this device right behind me, and I'm not trying to shoot like a home video and have my camera all over the place, so I apologize. But what it does is you have a speaker driver right here, and you basically have a laser, and the laser is measuring the displacement at very, very narrow increments, and the laser just moves all around the speaker diaphragm as the speaker diaphragm is moving, and it kind of maps it out, and so we're looking at that data right here, and you measure it at certain frequencies, and so what we're looking at right now is at 2 kilohertz, 2,000 hertz. The Neomin 5 speaker driver, the Gen 1 Neomin 5 speaker driver, Resonado technology, where we have the bobbin and the voice coil stretching along the entire length of the cone. And what you see is you get this consistent blue, and the colors, it's blue versus red. It represents kind of the which way it's moving, and we're basically seeing how it's all moving together. And that's what you kind of want to see. We're going to go up to 5 kilohertz, and you see it's all still one color. Red means down, blue means up, but we're just looking at making sure it's all moving together. It's pistonic. You do see here, like you see a little bit of irregularity from the speaker surround right here, and that is a mode from the surround, and we've actually it's a new patent, but you see, if you look at this surround closely, you guys see that like pattern.
Mm-hmm.
We call it there's an official marketing name for it. It hasn't been announced yet, but it's like it's the wavy surround, and that breaks up some of these modes and keeps the frequency response very smooth. If we go up to 8.5 kilohertz, we still see it's all one color, which means it's moving pistonically. If we were to look at like a speaker driver like this, you would have so many different color gradients, and half of this would be blue and half of this would be red. We have that data, and we've measured it and we've compared it. Obviously, I do not have it in this presentation. If we go up to, or we're still looking at 8.5 kilohertz, and you're looking at a little bit of a different viewing angle, but in the red and the yellow kind of represent the same thing. You see a little bit of breakup at the ends here, right? And that was because the voice coil that we had, it was not extending to the very end of the diaphragm. It was maybe going to like where my finger is on each side, and so you had kind of the diaphragm flaps were not being beneficial. This is looking at the same information at 12.5 kilohertz, and we're just seeing that continually pistonic behavior. And again, if you were to look at a speaker like this, it would be a lot worse. To go into some of the other advantages of FCS technology, we have, I was talking about the speaker suspension a little bit. What is giving you the compliance, the stiffness. And I had said for a conventional speaker, you have this spider, right, like a cotton material, and then you have the surround. Most of the mass in a speaker driver, speaker transducer, is in this voice coil. Some of it sometimes in the cone, and it really depends. But a lot of that mass is in this voice coil. And it's if you just think about it logically, it doesn't necessarily make sense to have both suspension components for a suspension above where the mass is. It's going to be a lot easier to rock. What we do with FCS technology is, and this is a decent view, we put the spider on the bottom, like this is FCS technology spider, and then you have the surround on the top. So you really get a more balanced mass in a more balanced suspension, more balanced compliance. Another advantage is there's automatically a symmetrical inductance and a symmetrical BL curve, and that's due to the fact of this planar coil, and you have two kind of electromagnetic speaker gaps where the top coil, the top part of the coil is in the top gap, and the bottom part of the coil is in the bottom gap. And because you have both of those, the two gaps kind of balance against each other, and they result in an inherently symmetrical inductance curve and an inherently symmetrical BL curve. Now, the BL curve.
Oh, yeah, I was going to say, are you able to go into just a little bit, like, high level, why that's important?
Yes, and I apologize. I should have started with that. The BL curve is looking at the BL it's measured in Tesla meters. It's called force factor, like the speaker force factor. And it's really telling you how strong the speaker motor is. You look at TL small parameters, and there's five that really matter. There's the moving mass of the speaker, what is the weight of the voice coil, what's moving in the speaker, the voice coil, the cone, the surround, and the spider. So that the moving mass is one crucial TL small parameter. The BL is another, and the BL is telling you like your motor force. Another crucial TL small parameter is your SD, your cone area, like how big the cone is. And then the last crucial TL small parameter I would say is excursion. Excursion is not an official TL small parameter, but it's an unofficial TL small parameter for those in the industry. But if we go back to the BL, I'm sorry, I got off track a little bit there. The BL curve is looking at your force factor over excursion. And so you're looking at as the speaker moves up, if we're looking at a speaker like this, as the speaker moves up and down, the voice coil is moving through the motor gap. It's the motor force is going to be highest when the coil is perfectly centered in that motor gap. But when you move the speaker up, or the voice coil moves up and the speaker excurts upwards, you're moving out of that motor gap. And you want to keep the motor force as even as possible as you go up and down through the motor gap. What the BL curve is showing us is exactly that. So you're looking at excursion, like how much it's moving, and then the force factor. And so we're seeing on this curve, at 0 excursion, the BL is 6. So we have 6, it's like a 6 Tesla meter speaker motor. It's pretty powerful. This is actually a BL curve from this NW7, which is going in that soundbar. So when the speaker's kind of at rest, the force factor is 6. But then when we move minus 4 millimeters, we're getting to like 5.7 force factor. And you want basically a very flat BL curve. And we're going to come back to this and looking at like system parameters and low frequency output, but you want a very flat BL curve. And so when the speaker moves minus 4 millimeters, we have a 5.75 BL, and that means that through you basically do not want, as the speaker moves really far up and down, for the force factor to drop substantially, because that is going to induce a lot of distortion, it's going to lower efficiency, and it's going to be really hard to generate low frequency performance. Low frequency performance is equal to literally just displacement, and displacement is equal to your cone area times your excursion. And if when the speaker is excurting a lot and your BL drops substantially, you're not going to be able to generate a lot of low frequency performance. If we look at like minus 8 millimeters or plus 8 millimeters, the BL is about like 3.25 Tesla meters. And that just means that when we start driving it that hard, we lose a lot of the force from the motor, and it's not effective at doing that. Does that make a little bit of sense?
Yeah, I think so. And then you want it to be symmetric so that you're getting kind of that same like force factor on either side.
Yes, exactly.
Okay.
Exactly. Otherwise, it's like the biggest distortion and that's actually a good thing to bring up. If you do not mind, I'm going to go off track a little bit. Well,
just a note, it's 11:36, so I just want to be mindful on of your time, but also on the hour. We're going to lose the room, so.
Sure. No, and I'll save it for the end if we have time.
All
This
right.
is looking at the inductance, and the inductance is not nearly as important as a metric, but that same reason you get a symmetrical BO curve, you get a symmetrical inductance curve. Now, this is probably what everyone is most familiar with, like just looking at frequency response data. The purpose of this slide is to show kind of off-axis frequency response data and the different characteristics from something of this aspect ratio. But if we position the driver vertically and we move, when you say off-axis measurement, you basically want to see, you're trying to determine how effective this speaker is going to be if you're not like listening to it right in front of it, if you're not right on axis or on the same plane with it. And that's very important, like in your living room, if you have bookshelf speakers and you're moving around, or you sit in a different place on the couch, you want very good off-axis response. And so you want very little deviation for off-axis measurements to on-axis measurements. And so this first chart is looking at if we place the speaker like this and we move the microphone across the horizontal plane. And so on axis, the microphone would be like this, right? And then off axis would be moving the microphone this way or this way. I think that makes sense. And so we see with this structure, this aspect ratio, it provides very wide dispersion this way. And you can see that just because the red line's 30-degree off-axis and the blue line is 60-degree off-axis. You see very little difference at higher frequencies. And I think you guys understand this, but at the as we increase in frequency, the acoustic wavelengths become smaller. And so at low frequencies where you have bigger wavelengths, it's a lot easier to get wide dispersion, or why you see no deviation between the lines at lower frequencies. But at the bigger frequencies, at the higher frequencies, it's much more of a challenge. If we put the speaker like this and we move the microphone in that same plane, so 30 degrees is 30 degrees, you're seeing substantial drop off. And this is a 5 dB scale, and 100 hertz, 1,000 hertz, 10,000 hertz, and you're seeing it like 2 kilohertz, this really nasty, like 30 dB deviation. That would sound terrible if you were listening to it, but you would never you would always use, in a lot of cases, if we're looking at like a sound bar and you put a speaker like this, you'd cross it over to a tweeter at like 2 kilohertz or like 1.5 kilohertz, just to ignore all this. We don't want any of that. And these off-axis characteristics are not due to FCS technology specifically. It's due to just the aspect ratio of the cone. And it depends a little bit per speaker, and it depends on like the cone material. This is like paper honeycomb, but it's the aspect ratio. So it's not necessarily on FCS technology, but you see that you don't want to be using a speaker in this aspect ratio full range. In this aspect ratio, however, you do. It's like, think about like you could have a really nice pair of bookshelf speakers like this. The last benefit of FCS technologies, you get a lot more power handling due to the planar coil, and you have both bobbins as a like aluminum heatsink, and so that enables you can drive the speaker a lot harder without reaching your thermal limits. This is kind of talking about, this slide specifically showing a structure we made to kind of a technology innovation to increase the bobbin, the voice coil stiffness. A circular speaker driver with a circular voice coil a cylindrical shape, that cylindrical shape and the circular voice coil, circular bobbin, you get a lot of inherent stiffness. Mechanically that's a mechanically optimized structure, or putting something in this cylinder is mechanically, it makes sense. It's a lot less stiff to go to just like a plane than it is that circle. And so one of the challenges we've had is trying to maintain that voice coil strength, because that is what's driving the speaker cone up and down. And so this is like a box beam structure mechanically, doing like two planes in two pieces of material in this box beam connected on the top and on the bottom, but also connected in the middle. It's called the box beam. It's a lot stiffer than a just inherently one plane. I wanted to talk a little bit about like how you evaluate a speaker driver, and I'll talk for 2 minutes on it. If we look at this Neowoofer 7, kind of that, the information here is outdated, and the Neowoofer 7 is finished. But if we look at the Neowoofer 7, we have listed here like 6 acoustic parameters, and these are kind of the acoustic parameters that you want to be looking at, how you judge a transducer. If you're looking at I want to build a soundbar, there's a lot of different, there's hundreds of transducer spec sheets and hundreds of different specifications that you look at, but like these are kind of the key that you need to look at. I had talked about like 5 golden teal small parameters. This is a little bit different, but they're very related. Like the SD is your cone area. The more cone area you have, the greater output you can have. It's simple physics. The greater cone area you can have, as I said, output in SPL. LM is like just a measure of output, your sensitivity, 1 watt, 1 meter. Your F0 is your resonant frequency. Your usable range is like your frequency bandwidth. Power rating's important, how hard you can drive the speaker, and then your excursion. The 5 golden small parameters kind of funnel into one of the 5 golden teal small parameters is effective SD, and the other is your X max, and the other parameters like your moving mass, your BL, kind of funnel into this SPL number. When someone says, "Oh, we want to make a killer soundbar," and I'm going to go really quick. When someone says we want to make a killer soundbar, we want to make a pair of bookshelf speakers. Any speaker designer, any acoustic engineer, the first thing they're going to go into their speaker box software. And what's on the screen right here is WinISD. And you basically take the teal small parameters of the speaker and you put it into the software, and it can tell you the frequency response that you can generate depending on your tuning parameters. And so this is looking at the actual parameters from the soundbar project that's going to be released with a major home audio brand in the U.S. It's a very historic audio brand, but one who has a lot of customer recognition with this speaker driver. The red line is if, and so I guess when you take this box simulation software, you first put like how big your box is. And as the box gets bigger, you can generally get better low frequency response. And you guys kind of talked about ported and passive radio stuff, but we're working with like a 4.7 liter enclosure, and we're working with 80 watts of power from the amplifier. And those are 2 things we worked with the brand to decide and determine and off of this initial simulation. But you basically enter the teal small parameters, and then you get this red line, and the red line shows that at like 50 hertz, we have about almost 100 or a little bit more than 100 dB of output at 50 hertz. Normally, most soundbars, like a lot of Samsung soundbars, they're not getting 100 dB to like 100 hertz. A challenge with soundbars has been getting more low frequency output without that separate subwoofer, and the solution that FCS technology enables is higher like you can use this is like a subwoofer driver for a soundbar a little bit, but super high excursion. It also it's like a mid-range driver and a subwoofer driver, and that with paired with tweeters, this can enable like a really wide bandwidth for a soundbar. And what we see is a very good low frequency output. We have entered, you can see we have a fourth order high pass at 39 hertz. And then we have a couple parametric EQ things to kind of tune down this peak that you see in the red line, and it results in the blue line. This is showing another view from that box software, and it's showing like the cone excursion. The excursion is not something that is, you read like a speaker textbook or it's not something that's taught, but it is the number one, it is the number one speaker transducer parameter. If you're looking at a transducer and you're like, how do we get bass? It's all about the excursion. And not a lot of people realize that. And you can usually tell if you go into like a meeting and someone has like a spec sheet up. And if it has excursion, excursion is like how much it's moving. The specific specification we use is Xmax XBL at 82%. And it's basically, if we go back to that BL curve, it's at what point is the BL at 82% of the peak? And so 82% of 6 Tesla meters is like 4.8 maybe. And so if we go to 4.8, you see it's like -6 and then +6. And so that's like the XBL at 82%. That's the excursion spec. But if the last thing I'll say is if you're looking at a transducer and you're looking at a something and they don't have the excursion listed, they don't really know what they are talking about. It's all about displacement, how much you can move the speaker and the amount of air you can move. I covered a few different topics there, and I tried to keep it not too technical in the weeds, and tie it back to real life. But what questions, where could I expand further? Where did I lose everyone?
Well, yeah, I thought that was like an excellent summary of a bunch of really important things. I was kind of curious because it looks like this is a more premium kind of like target is what you're looking at. Like I could see this being used in products where people really care about like the hi-fi kind of stuff, but it's also about form factors. So is that the target? Am I correct in that assumption?
Oh, so FCS technology, it's all about high performance in the high aspect ratio form factor. And I probably did not make that clear thinking through how I went through the story. And so you can look at like current soundbars that are 3 inches tall, and we can put a driver in there at that 3-inch tall height that performs better than the other speaker drivers. So this is a Samsung speaker driver that they use like pretty unanimously, and it's pretty close to like the height of this, and we can put this in that same soundbar and match the form factor but enable better performance, or we can lower the height of the soundbar, improve the form factor, make it a sleeker design, and maintain performance. And the way, if we're looking at like the example where we're taking like a 3-inch tall soundbar and we're replacing the speaker driver to improve the performance, when you take a speaker like this, it's very difficult to get a lot of excursion, because to get a lot of excursion, you need your suspension to be very linear as you move like plus or minus 6 millimeters, because you need it to move very evenly and things. And it's difficult when you have a circular voice coil, and if this is a little bit difficult to explain, but it's difficult to get that excursion with the conventional speaker driver because of that way the circular voice coil is structured and how circular spiders are done. So with this example, where basically we can increase a lot of the excursion and get better low end. And so this is a $400 MSRP soundbar. It's very similar like the Sonos Beam. That's like there's a JBL $400 all-in-one bar. So it is a premium. $400, I'd say, is I call that category premium mass market. Uh, uh, we call that category premium mass market. If we want like we could like the Sonos Beam is flat out. When I say flat out, like at what frequency is your frequency curve going to be flat? And like Sonos Beam is like 70 or 80 hertz. So this is enabling it to be flat out closer to 50 hertz, 45 hertz, and it's premium, but not too premium. Does that answer your question a little bit, Alex?
Yeah, that helps. I'm curious, we've got time probably for like 2 questions. If you guys have anything that you're kind of wondering about, or anything that maybe Peter said that you're like, can you go over that again? If, yeah.
Feel about them having summer.
Yeah, that was going to be my kind of my closing question in a sense, but I'll just jump to that. So yeah, I sent out the email for like the 2 job descriptions that you sent. One of them is a transducer simulation engineer, and then one of them is a junior systems architecture and testing engineer. And so I think it's always helpful like to talk to people in the industry, because what you do in school looks very different from doing an actual job. So are you able to maybe kind of illustrate what those are like, and like what that job looks like?
That's a great question. That's a really good question. So if we start with the testing and the system architecture and testing engineer, designing a transducer is extremely. Resonado was trying to design reference designs for FCS technology transducers that then our licensees can adapt and slightly modify per product. And the reference designs are supposed to kind of serve as examples. But to make that reference design, you really need to have a good understanding of the end product constraints. So this transducer was targeted at a soundbar from the start, and like we had to make a lot of assumptions, and we had to do a lot of measurement and benchmarking it to figure out like what are the end parameters of the system, what experience do we want the customer or the person who's in their living room listening to this to have, and then you need to like make assumptions on the system parameters that you'll be able to generate, and then design the transducer from like those lists of target specifications, assuming certain system requirements and to deliver X end user environment. So it's very important. You need a really good system understanding, like a very good understanding of soundbar internals, like soundbar amplifiers, soundbar performance, the end user experience, and just in order to start a transducer product, as we need to be positioned well. So the system architecture and testing engineer is going to spend a lot of time looking at soundbars, smart speakers, and the system as a whole, and that is guides to the decisions we make from a transducer development standpoint. How much excursion do we need this transducer to have? How much SPL do we need this transducer to have? What type of frequency range does it have? And that all needs to come from like the end system. It's like trying to develop a component for trying to develop a very optimized component for a system that is not yet defined. And so they would be spending a lot of time in this lab measuring both Resonado transducers, like benchmark transducers, like some of the things I was holding up, and then just looking at the system side, being very familiar with different soundbars. Doing like this type of box simulation is important. The simulation engineer is going to be looking at the electromagnetics and designing like the speaker motor. How big do our magnets if the system architecture and testing engineer comes up with like a list of, okay, we want to make a driver that's positioned for this industry, what are the parameters that we need? It's like, okay, we want 80 dB. That's what the system person says. The simulation engineers are going to be looking at, okay, how big magnets do we need? How big of yokes? What's our motor geometry? They're going to be using multi-physics software. We use COMSOL, but we also use a couple different programs to really design the speaker motor, the speaker voice coil, the speaker suspension, and we've old speaker engineering, old transducer engineering, conventional traditional transducer engineering is like looking at, it's like, oh, we want a speaker with a little bit more SPL, let's put a little bit of a bigger magnet on it. That's a lot of what they do in Asia, and they have done. Nothing against Asia, but it's that's kind of like the less advanced engineering, and it's what you see when you go to like some of these traditional Chinese speaker factories. But kind of the new wave of speaker engineering, and like what Harman started doing and what Sonos does, is using multi-physics software like CompZone. You get really, really into the nitty-gritty with all the different parameters and all the different specifications, and you really parameterize and simulate and design something for those parameters, and then it makes the product development process a lot easier, because our goal is to make our simulation models the most accurate as possible, and we're constantly validating that. It's like a looped cycle, and that enables us to have to like actually build and prototype a smaller number of times in order to reach the parameters that we want. Does that make sense, or give a decent overview of what those two positions would be doing?
Yeah, I think so. Awesome. Yeah.
I must say, if I can say, well, so I don't know if Peter like is maybe in the main process of like designing through like hiring and stuff, but like what might be stuff that like if you wanted to get into those positions and hire for them, what are some things that you're looking for in a graduate student or a senior that that makes you want to hire that person?
That's a great. I think the
like what type of experience are you looking for?
and it's in not and I would say that on the experience level, if people have built a speaker before, that is like at least they've like, especially if it's a hand or it's a self project, that shows a little bit of interest and desire and being proactive. But I'd say generally the characteristics are just curiosity, wanting to learn. So much of the speaker industry is like, in a specific to stuff I've been talking about, it's passed off person to person. There's no books on it. There's 200 people or 300 people or 400 people in the industry who are very experienced at it, but no one's teaching it really. It's all like word of mouth a little bit, and so it's all about learning. We want people who are passionate about developing new things and passionate about like innovation and passionate about just like working on a team, but who are really curious, who want to learn. And we don't really, for one of the positions, some of the job descriptions, they have different levels of preferred experience, but just reach out to your resume at hello@resonado.com. hello@resonado.com. I get, and I'll just write that right here in case. I get all those inquiries, and I'll respond to each one. I believe there's a couple individuals from the AES Cal Poly program who have reached out, who are in the pipeline, but reach out with your resume. Some of the positions have experience required, but we really just want willing to work hard and be curious and learn, because there's not a lot of, there's no way we can ever get someone from like expect a senior, one of you guys, to know much, just because it isn't taught.
Gotcha. Well, awesome. Yeah, so everyone definitely reach out if this is something that interested you. Peter, this was an excellent overview of like kind of deep dive into a bunch of different speaker technologies, and like both some things that already exist and then a lot of the cool innovations that you guys are working on. So thank you again. Thank you for your time. And
Thank you.
yeah, look forward to hopefully having some people reach out to you.
Thank you very much. We appreciate it.
All right.
Have a great day, everyone.
All right. Take care. Thanks. Bye.